Hello everyone. Good to see you again. I hope all of you are doing very well. In this video, I'm going to introduce macro marketing data. Before you start, don't forget to check out our course website for if there are readings and videos required for this lecture. In this lecture, I start with demand prediction for firms' decision making. Next, I'm going to introduce two basic concepts of unit in analysis. One is unit of observation, and the other one is unit of analysis. Then, I'm going to talk about what is macro marketing compared to micro marketing. And I'm going to introduce several data sources for macro marketing data. Last, I'm going to present a classic of marketing science with macro marketing data, the Boss Division model, as an example. Are you ready? Let's get started. Demand prediction is the key to firms' decision making. Most firms make a decision based on ROIs of choice options. The ROI is a formal way to evaluate what would happen with an action, and marketing managers choose the action expected to provide the best outcome. The return consists of various tangible and intangible components, but the managers in most firms focus mainly on profits or revenues from the action considered to do. Thus, accurate prediction of demand or sales, conditional on doing the action, must be the key to ROI analysis and decision making. This process is formally called counterfactual in marketing and economics. The gold standard of counterfactual is experimentation. Pick a group of samples for each possible action, do the action, and observe the sample's responses to the action. However, it is not always feasible to conduct an experiment for some reasons, like a limited budget and legal and moral issues. So, marketing researchers have focused on historical data, where consumers' responses to marketing actions actually executed in the past are recorded. Reflecting the past responses in the historical data, we can project what would happen to consumer demand. In the data, managers have made decisions on the various states. Taking a look into the cases by action and state, it is possible to examine and evaluate what would happen to demand. This is a process of calibration before shooting. Once we calibrate our weapon, we are ready for shooting the demand prediction. And our shot absolutely depends on the action we consider and the state we face. Then, what if the calibration was not good enough to project the demand? For example, what if we need to make a decision under a condition we've never experienced? In this case, prediction based on historical data may not work well. In other words, what we can predict is within the scope of what we have observed. Here is a toy example for better understanding. Let's say there are 4 customers, and this table shows historical observations of their demand for a product with 2 price levels, $4 and $5. Those customers show different demand levels and price sensitivities. Customers 1 and 2 are heavy users, showing a higher level of demand than customers 3 and 4. But, in response to the price increase, customer 1 reduced her demand more, implying that she's more price sensitive than customer 2. Now, let's take a look at the demand change in total. In total, those customers cut down the demand by 20%, which is not the same as each individual customer's response to a price change. That is, if only the market level observations are available in the data, such data reflects the average demand responses. Thus, what we can predict is within the scope of what we have observed. If we observed only the total, not the individual customer's demand, what we can predict is only the average response. If we observed only one customer's demand, her demand response is the only one we can predict. This relationship between what we observed in data and what we can predict can be conceptualized as unit of observation and unit of analysis. Unit of observation is the set of dimensions where each observation is defined. For example, the grocery store's scanner data contain information of which product was purchased by whom on which date. Unit of observation of the data is a product individual time level. So, unit of observation describes what was observed or collected in data. Unit of analysis is different from unit of observation. It is about what to know to solve a problem. For example, let's say a grocery store wants to know who is the best target of a discount coupon campaign. To solve this targeting problem, the store should evaluate each individual customer's profitability with the discount coupon and find the customers with highest expected profit. That is, unit of analysis must be an individual level for the targeting problem. Unit of observation and unit of analysis provide clear definitions of micro and macro marketing. Micro-marketing focuses on individual customers' behaviors. The main research question is to identify which factors drive individual customers' choice and demand for segmentation, targeting, and positioning strategies. Thus, both unit of analysis and unit of observation are at an individual consumer level. But macro-marketing focuses more on the overall market fluctuations. Although there are various research problems, most of them are engaged in strategic decisions based on the prediction of a market. So, market or aggregate level observations with relatively low frequency are mostly used. Prediction using historical data has long been studied both in academics and practice. Internally recorded own price and sales data are easily available, and so they have the longest history. They are the basic and the most important data we have to look into for demand prediction. In addition to the internal records, regular public surveys such as census have served as a good supplement. Also, governments, public associations, and organizations have regularly announced some of aggregate level information, such as the number of vehicle registrations, the number of new car shipments, and retail gasoline prices. These variables could be good predictors for vehicle demand and sales. Some commercial data also have long been used for demand prediction. Research firms such as Nielsen, Kantar, and IRI have hired their own panelists and continuously collected and updated the data. Those data are sometimes expensive, but cover a large number of customers, products, stores, and markets. In addition to the classical data sources, we now have other data sources by recent advances in information technology. Particularly, the World Wide Web makes both firms and customers leave digital footprint. Researchers have developed bots to track those digital footprints 24/7. Camel, camel, camel is one of examples. This is a screenshot of camel, camel, camel webpage. I copy and pasted the Amazon page URL of an East product, and the web page shows the price fluctuation over time that the bots have tracked. As you can see, there is a huge surge of the price in the middle of March 2020 when the coronavirus pandemic started. Another example of information technology applications is Haggle, which is a data sharing platform. This is a screenshot of Haggle's webpage. It has an interesting feature, which is called competition. When a data provider shares data with the public through Haggle, she can set a goal of the project with a prize. There is a famous example of the competition. Several years ago, Walmart shared its sales data with the public and opened a competition for the best sales forecasting performance. As the prize of the competition, Walmart hired the winner as a data scientist. The application of technology is not limited to historical data. Information technology allows us to conduct a series of experiments online. The most popular service is Mechanical Turk by Amazon, MTurk for short. Nowadays, most behavioral academic studies are conducted through the MTurk. The technology has changed not only data mining, but also consumer behavior itself. Now, think about your purchase behavior. When you feel a strong need for a certain product, what do you do first? Highly likely, you do Google it first. That is, if there is a herd to a product, we may find a strong signal of the herding in Google search queries. So, Google quickly caught this and launched Google Trends service in 2006. This is a screenshot of Google Trends webpage. When I put an interesting keyword, Google Trends shows popularity scores of the keyword over time across different regions and different languages. For example, the screenshot shows the search trend for coupon for the last 5 years in the United States. Can you find Black Friday seasons? Yes. Those 5 spikes are Black Friday and Christmas seasons over the years. The change in consumer behaviors is not limited to information gathering. It is much easier and more convenient to communicate with others online than offline, so people share their opinion, evaluation, and experience after using a product and generate some idea, feeling, and thoughts that potentially lead to their needs, wants, and demands. That is, consumer communication in online marketplace and social media can be a strong predictor of consumer demand. Alright, so far, I have introduced basic concepts related to demand prediction using historical data and several data sources to be used for the prediction. Now, I'm going to introduce a classic example of demand prediction, the Bass diffusion model. The Bass diffusion model, first developed by Frank Bass in 1969, has long been used to predict what will happen once a novel product like a high-tech product is introduced. This is an example. Upright Go, a posture correcting device. I have a back pain due to my really bad posture, and my wife bought this device to correct the posture. This is a small device that can be easily attached on the middle of my back. When I get out of alignment, the device detects it and vibrates, making me immediately correct my posture. Then, suppose that you are the product manager of this device. Once you launched, you may want to know how many people will eventually buy the device and how fast or slow the potential customers adopt the device to develop marketing and operation strategies. From a small number of initial sales data, the vast diffusion model draws a prediction of market penetration. The vast diffusion model is widely used not only for the high-tech products, but also some entertainment products like movies. The main idea of the vast diffusion model is as follows. In most cases, adoption of a product shows an S-shaped curve. Once the product was successfully launched to the market, people may herd to the product and sales may explode, which is called a takeoff. After the takeoff, the adoption continues for a while unless most of the potential users adopt the product. Once saturated, the adoption curve shows a flat shape. Then the vertical height of the adoption curve denotes the potential size of the market, and the length of time period spanning from the launch to the saturation measures the speed of the adoption. When we forecast the adoption through the BOSS model, we have only a few observations. Quick question. What is unit of observation? Each observation is unique to the product at a time period in a market. Based on the short observation, we want to predict the shape of the sales of the product in the market over time. So, unit of analysis is the same as the unit of observation. And please keep this in your mind. Each individual customer's purchase is neither observed nor to be predicted. But the model built on assuming representative types of individual consumers adopting behaviors. Let's say there are M of potential customers. This is assumed to be constant over time. At time t-1, there are some people who have already adopted the product. Denote the number of those adopters and t-1. The remaining portion of M is the number of people who have not yet adopted but potentially adopt the product at some day. Then, let's think of what happens during the next time period. During the next time period, time t, some people adopt the product. Broadly, we can divide those new adopters at time t into two segments. Some of the adopters might purchase the product due to ads and mass media, but others might be influenced by those who already adopted through word of mouth or social interactions. In the BOSS model, the former type of new adopters is called innovators, and the latter one is called imitators. The model assumes that the likelihood of a new adoption is given by P plus Q times N t-1 divided by M. The first term, P, is the rate of innovation, which is assumed to be constant. The second term, Q times N t-1 divided by M, is the likelihood of imitation. Imitation is basically coming from interpersonal communications with past adopters. So, N t-1 over M indicates the possibility of the communications. Letting Q denote the success rate of imitation from each communication, which is assumed to be constant, we have the rate of imitation by multiplying n(t-1) over m by Q. Multiplying the sum of the rates of innovation and imitation by the number of non-adapters at time t, we have prediction of the number of new adapters as t, which is given by p plus q times n(t-1) divided by m times m minus nt-1. Then, what is the correct interpretation of the model? Both unit of observation and unit of analysis are not individual level. Therefore, we cannot make an individual level interpretation. Instead, the model assumes innovating and imitating behaviors, so the interpretation of the model is conditional on validity of the assumption. If the assumption is true, we expect that, on average, P plus Q times n(t-1) over m times m minus nt-1 of adoption will happen at time t. This is a classic example of model-based prediction for aggregate demand and an example of macro-marketing analysis. Alright, that's all I have in this lecture. After watching this lecture, please check out our website again for if there are additional readings and videos required or strongly recommended, online quiz assignment, and hands-on exercise in our software. Then, see you in the next lecture. Bye-bye.